Okay, back to the soldering iron station. So, in my last video, as you saw, I damaged the element, and that's the element. The only successful part was the spot weld, and you can see the spot weld is very strong. It never came off. Anyway, so here is what's going to happen. I said I would buy an original Weller element, but in this case I haven't done that, and I'm not going to be doing that because it's way too expensive. It's not worth the money, in my opinion. Now, what I might do in the future, okay, is that's where the element actually is wound, on top of this pipe. I might buy a fiberglass thread which can handle around 600 degrees and wrap this fiberglass around the nichrome wire and have my own insulation, and maybe one day I'll make another video rewinding this back with the fiberglass insulation. Now, I said also that you cannot buy the insulated nichrome wire. Well, in Australia, you cannot really buy it now. But in Germany, I found a place in Germany where they sell it exactly like this for the right size. I think it's about 2.1, they want 2.2, sorry, 0.21 or 0.22 thickness with insulation on it, with the fiberglass braiding on it. Now, again, to get that stuff from Germany, it's way the freight will cost more than a whole 2 soldering iron stations brand new. So that's not worth doing. So what I did instead, again, just to do the software, just to have at least the software, I have bought a brand new element, but it's not a Weller one. This one is by XY Tronics, and the model on that is 168-3C SIA or 1A60, which for the 60 watts. This one is a bit more powerful than the Weller one. I think the Weller one really is around 48, 50 watts if you run it at 24. This one is about 60 watts. Now, this is much cheaper to buy. I think this was around $30 Australian, okay? This system is very similar to the Weller, which means it's got a winding with nichrome wire inside, and it's got a thermocouple built in. So I will not be using the thermocouple that I was building, okay, because this one has already got it. But in the future, if I will get another Weller original, or I'll wind back this up, the software will be exactly pretty much the same. These are the most accurate soldering irons you can get, because the ceramic type, for example, this, I have a micron here. This uses a ceramic that's the heater there. It's ceramic heater with a winding inside. Now, this is pretty good. This is it's not one of those cheap Chinese ones. And even the size, it's not too loose in the... But these ones are harder to control, because this one, I'm not sure how the thermocouple is. It's probably right at the edge, which is good. But a lot of the heaters you buy with these ceramic heaters from China, they will never work properly, because the thermocouple, especially the ones, there's two types. One is like a thermistor, and then they have the K-type thermocouple. The thermocouple is inside the element. It's not on the outside of the winding, it's on the inside, which means it will be inaccurate, which means you have to estimate and measure the temperature of the tip, and then you got a minus maybe 100 degrees difference between the outside and the internal part where the thermocouple is. The good ones, I'm not sure how this is made, the thermocouple should be right at the end, separate to the element, okay, or on the outside within the ceramic, on top of where the element winding is. So anyway, the video is not about this, but that is why these ones have to keep pulsating and, constantly off and on, because otherwise you can't control the tip. But this type, or like the Weller, it's where the thermocouple is more accurate, and you'll have better control. So the good thing about this fits in the Weller holder. And just to show you that it does, you can see the actual holes do line up. Okay? They do line up exactly right. So now, the other difference is that this one uses a longer shank on the tip than the Weller. So the Weller is a very short tip, and the winding, as you saw, is very short. Okay, so I will be using this, and I'll carry on with the software so I can finish the project. Okay, so I will be wiring this up and installing it in here so it's not loose like the other one. Don't want to damage the heater wires or anything like that, or the thermocouple. And then we'll take it from there. Okay, so I've ran the wire into the holder. This is, of course, not the original wire. I had this wire from a desoldering station. So it's actually got more than enough wires. It's got 2, 4, 6, 8. These are the movement switch that I've got. Okay. I'll try to put the number of that. Don't have it off by heart right now. So I'm going to have a little circuit. Okay. Okay, and that's the switch soldered there. I'll have to clean that up a little bit. And I will be just probably hot gluing that in the bottom of the circuit board like that. Okay, so the connection is made. The two red ones are the heater, and I've used the white and a yellow for the thermocouple, so I know which one is the positive. So I used the yellow for the positive. Okay. And the movement switch or tilt switch, black and blue. And I just glued that little circuit board where I soldered the movement switch on that little board there. So that's put on there. Okay. So here I have the software pretty much done, and the circuit as well. It's almost done, but I've reconnected here rewired the circuit, because the way it was with the triac, that was never going to work running off the picture the way I had it. So this is the correct way, and I am using the zero crossing reference chip. That's the best way to run it. I'm leaving everything on to be on AC, and so that's how it's wired. Okay, and I might not use the buck converter. I might put a 12-volt regulator here, and then the 5-volt regulator. I might do something like that. I'll see how I go. Also, the switches, I added an extra switch. I haven't actually wired it yet, but I was thinking of having a switch to save the values in memory when I press the switch. At the moment, I've got the software that it automatically saves the value of the set temperature, and just with when you're in program mode. But I thought it might be better if you have a separate switch. Pretty much the circuit here is still roughly the same. This capacitor here, I've changed it to 470 nanofarad, which gave out a stable regulation with the pot. And the voltage out of this output, I've just got the 100 nanofarad. I could increase that as well. Yeah, and that will make it a bit more delayful changing slightly. Anyway, back to the software. So from the last video when I did the software, started the software have changed a lot. So here we have an interrupt LED. It's only for a reference for doing the programming. I can install it or not install it, it's more important. The set LED, that's the same. I've got the heater output on port C, .5, channel 5, and the set switch. These are all the extra variables I added. I've got a, I think that was already there. I've got a sleep flag now because it actually goes to sleep after half an hour if no movement has been sensed on the soldering iron here. And now I've created a clock to be able to measure the timing of the sleep when it goes to sleep. So I've got ticks, which is milliseconds, and then I've got seconds and I've got minutes, and that's pretty much all I need for the timer. Then I've got the temp. I've already said these, had these before. I've got one timer one. This is to load a variable into the timer for the interrupt, because now I am using interrupts to go and read the temperature and set the temperature. It's all done in the interrupt. And also the set switch is actually read with an interrupt as well, with the interrupt on change flag. I've got a tip error now, so I'll be able to adjust the tip error. And I've got digital letter here. That's for the C, where it shows C in the digits, the last digit. But I can change the letter to something else. I mean, it's limited. It's only really made for digital numbers, but that's why I've got a variable there. I've got a variable called EEPROM value. That's just to read from the EEPROM. Okay. The counter I had, I think I think that counter was a byte before. Now I made it a word, so it's 16-bit. And I've got delay time. flash X is to use a for loop, and flash count. So these two bytes work together in a for loop. And here we're gonna read from the EEPROM and put it in the set temp. So that's the temperature that I have saved in memory, this set temperature, and I've saved the tip error in the memory as well, in the EEPROM. Okay, so around here I'm using timer 1 to be able to time when I go to an interrupt. And just to show you on the oscilloscope, when it goes to an interrupt, it actually turns on an LED or an output on the chip. And you can see here the LED flashing. That's it. That's every time it goes to an interrupt. And if I could zoom in on the oscilloscope, okay, you can see it's going in interrupt every 111, okay, 0.6, 0.5, okay. So yeah, I've got the circuit there running. I've got the module, thermocouple module, and I've got just a triac. I haven't made the circuit exactly, but what I've drawn is pretty much what's inside here. The triac driver, this has got a zero crossing reference in it, and I've got the pot here, okay, and I've got the new element there with the built-in thermocouple. Back to the software. So here we have timeout, and the timeout exception, not a variable, it's a constant. It's set at 30. That means 30, that's going to be equal to 30 minutes, okay? So when it counts 30 minutes, goes to sleep, turns the iron off. And then when you move the iron back on, it will turn back on, and it starts counting again. And every time you're moving the soldering iron and that switch is sensed on the interrupt and change, it will zero the counters and it keeps recounting. So the only way to reach 30 minutes is when there's no movement at all on the iron. So here I made the software to flash the LED screen with the temperature set temperature that you saved in memory and what the error calculation is, because you can change that if you want to recalibrate the tip, okay? And so that was done for that reason. So anyway, so I can show you here when I turn the power off, okay, and you turn it back on, it's going to flash the error calculation and it's going to flash whatever you saved in memory, the temperature in memory. So that's the 12 degrees and 250 degrees. Now it's reading the real temperature of the iron, okay, and that was doing the averaging there, and it's reading 24 degrees. So that was done here. So I've changed the letter to negative when I was reading the tip error. That's what it flashed. And here I told it how many times to flash, 2 times. And then I've told it to go and flash the actual display. But first I had to set the values. And when you come back, I'm delaying 1.5 seconds with that display, so it gives you time to see it. And then I changed the negative letter that in the end to a degree, a zero, a small zero at the top, And that now we're going to show the value of the temperature setting. So you see I said here value equals set temp, and then flash count 3 times. So it flashes the screen 3 times, and when it returns, it delays again 1.5 seconds. And then change the letter to a C. And that's what it's showing now. It's showing a C, okay? As you see in the bottom. And just to show you again, okay, when you switch it on and turn it back on, it's a negative. Now it's a degree. And now it's a C, and it's reading Celsius. It's all in Celsius, but I just put that change just so it indicates you're in a different mode and all that, just to better reference for your eye, since it's not an LCD screen. And yeah, okay, back to the software, and this turns on the global interrupts. That's a hex number. Enable unmask all unmasked interrupts. So this is all regarding the pick chip registers, and enable timer 1 interrupts. So that's what that is. And I'm using the onboard interrupt system of PIC Basic Pro. So on interrupt, go to int. You can change this name whatever you want. You can call it my int or any name you want. And the main loop is here. So when it's running at the moment, I'm not pressing any switches, I'm not changing temperatures or anything like that. This is where the main code is pretty much running, okay? So it updates the value before it decides to go to the average, or showing the LED out on the display, because I'm coming from an interrupt, okay? Because it's constantly, keep in mind, every 111 or 112 milliseconds, it's going to an interrupt and it's returning here. Going interrupt, returning here. Constantly doing that. And the reason why I did that, so no matter what, if I'm in the setting, changing the temperature, for example, if I press the switch and I'm in changing the temperature here with the pot, okay, you can see what I'm changing. Let's see, I'll set it to 100. While I'm doing this, it's still going to the interrupt, the program, and it's still regulating the temperature. So if you don't do that, then if the heater is on the off state, on the on state, then it will overheat, because if you're not going and reading the temperature at the same time while I'm changing this, you're not controlling the iron. So I thought it was best to, you still can do it without going to the interrupt, but you'll have to have in the loop, let's say when you are in changing the temperature, which is here, the loop of change, you'll have to keep telling it, go and read the temperature and adjust the temperature, okay? But instead of keep on calling out a command in this loop, the interrupt is doing that for me. Okay, so I'll just show you this. For example, now I'm going to set a new temperature of, let's say, 100 degrees, okay? It's flashed, and hang on a minute. The switch is a bit loose here, so when I'm clicking it, it's breaking contact. It's just on the breadboard, and you can see, look, it's just come off there. So that's what that is. Back to the software. So the main loop, this pretty much was the same from the first code that I did. So, and here when it goes to an interrupt and it actually reads the switch, when it returns back, if the set switch is toggled, that variable, and it's a 1, then you go to and set the temperature. So that's what this line is, and put the LED on. So that's what's happening there. Go to temp settings. And also, I'm delaying the code here for 200 milliseconds. Reason why I did that, because I don't want to keep constantly updating the LED screen. Okay, so I'm delaying to update the LED screen for 200 milliseconds, and that's what this section is doing here. And I only do that once the temperature has equaled to the set temperature. So delay 100 milliseconds between LED screens updates, okay? But let's say if I set it to 200 or 300 degrees and the temperature is still at 100, for example, then it will not delay, it will update quickly, and because the temperature is going up high and you want it to update visually a bit quicker, so you'll keep up with the temperature speed of rise, okay? But once it hits the temperature, I don't want it to keep updating that quick. So that's what that's for. So from here, I'm going to go to where the interrupt is, since it's constantly going to an interrupt every 112 milliseconds, and we'll go to where the interrupt loop is, and it's right at the bottom here. Okay, and it's here. So we come to this position, and here this command just disables the interrupt. Okay, ed, that's where it's called int. So the first thing we're going to do, since also the switch is sensed by change interrupt on change, this interrupt on change, it will interrupt whether the switch gone from high to low or from low to high. There's no settings. You cannot choose to go to an interrupt, let's say from high to low only, or from low to high only. There's no settings on this particular chip. It just doesn't have control on that. So whether it's gone from low to high or from high to low, it knows all it's going to sense that there has been a change, and it will come to the interrupt and will come here. So you want to be reading that first. So that's why I've put it first thing here in the interrupt. So if the switch is pressed and switch flag was cleared, then toggle the temp set flag. If it was a 0, it's a 1. If it's a 1, it's a 0. I've already explained this in before. And if you release the switch, every time you come to interrupt, then it's going to know that you release the switch here. Every 112 milliseconds, it's coming here. If the switch wasn't pressed, then it was just the normal 112 milliseconds timer 1 interrupt, and so it will ignore that, and it will put the LED on, and that's what you're seeing here, these pulses. That's where that is created there. And you can see how the pulses are not moving, right? So that's pretty stable, the interrupt. Then we're doing the error correction calculation. Each time you read the input, and here I'm reading the AD8495, which is on that analog 2. Now the error correction. The error is there, by the way. only because it's a soldering iron. So where the heater is, the element is, that's always going to be hotter than the tip, because that's where it's heating up here on this side. The further out you get, the colder it is. So from the distance, from that point to where the thermocouple is here, there's a distance. So because you have the element nichrome wire heating here, this part's always going to be hotter than the end. Therefore, that's the correction. Now, if you switch off the soldering iron and you are not heating the element, then the error goes away. That means whatever the temperature is here, the same temperature will be there, pretty much, yeah, because the element is not on. So the whole metal here will stabilize for the same temp. Okay? So that's what you have to keep in mind. So that's the reason of the error correction. So getting back to the software here, where are we? Yep. So this it minuses whatever the tip error is of the main temperature. So that's what that's doing there. And here I also found that over 300 degrees, okay, I found that I had to minus again another 5 degrees, okay. So I did that there. Equals or greater than 300 minus another 5 degrees. So it's a bit of a current temperature adjustment again. Obviously, when this is getting hotter here, then something is changing in the metals, and so I needed to do that to have it more accurate. Not much, only just 5 degrees. So that's what I found. So I did that accordingly to what my testing were. Otherwise, normally you wouldn't have to do that. Yeah. Then here we're going to check if the temperature is over the set value or under. So every time it comes here, it's reading the temperature, and now this is what puts the heater on or off. Okay? So you don't get bored just not only showing you the software, you'll be seeing the, I'll be showing the performance and the control of the soldering iron. So here we go. We'll put it on. Okay. And at the moment I have set the setting to 250 degrees Celsius. And I'll be measuring with the thermocouple as well. So I'll put the external temperature reader. So the red displays the temperature of the soldering iron. Okay. And that's reading 250. And my external one was reading about 250 as well, as you can see there. Okay. It's showing a bit more because it depends how close I have it to the edge. So if I bring it a bit more to the edge, it's 250. The readout, it's saying 251 in the red. That's the controller. Okay, now it's gone to 250. You can see. Very accurate, and it's stable. Now, if I change the temperature, so we'll go into setting mode, and we'll change it to 275. Okay, I stored that the blue setting LED flashed because I stored that in memory. Okay, You can see there 275, 275. Okay. So it's keeping it very stable. We'll go up to 300 degrees. Okay. Store the new figure. It's actually already gone to there. Put some new solder. You can see there it's pretty much the same. 300. Okay. Depends how far I am to the edge of the tip. Okay. So getting back to the code, and it checks if the temperature equals or is greater than the set temp, then switch the heater off. And if the soldering iron is not in sleep mode, okay, once it's in sleep mode, the software is still running. I made it, it doesn't stop, but it's not putting the heater on. So if the sleep flags equal 0, then you can turn the temperature on only if the temperature is lower than the set temperature. Okay. So if it's smaller, then turn the heater on. Okay, and then here you load in, you stop the clock and you load timer 1 register with the value of the 10,000, and that's, you got to do it in 2 steps, and that's what that does. This thing here, it's for the clock that I've created, ticks. So every 112 milliseconds, okay, I create, I'm adding 1 to the ticks value, and every 9, okay, if you times 112 times 9, you get around roughly just slightly over 1000 milliseconds, okay, which equals to 1 second. And that's for the timer, it's measuring when to go to sleep, okay. And once ticks equals to 9 or greater, this is just an assurance here, just a guarantee, just in case something goes wrong. It's never really going to happen, but I always like to do that. So normally it's always going to equal to 9. It's going to be able to read that. But let's say something happens to the code. Let's say you do another software. I do this by practice. I always like to say if it's any or greater, okay, that means, this will be true. Then 0 the ticks back to 0, okay. Here I explain 112 milliseconds, every interrupt times 9 equals roughly 1 second, okay. Then seconds plus 1 now, the first second, then when you read 59 seconds, greater than 59, which means 60, 0 the seconds, and count 1 minute. So that's my clock here. And once, if the minutes equals or greater than the timeout, which I set it to 30 for 30 minutes, then turn the heater on, or off, sorry, if it was on, okay, because we do not know whether over here, whether the heater was in the off position or on. So just to make sure, you need to turn it off and set the sleep flag to 1. And that's how I know that it's gone to sleep, and 0 the minutes, back to 0, okay? And clear the flags, the interrupt flags, just before you resume back to the code. And resuming back to the code in this situation, if I was in the main loop, then it goes to the main loop. If I was in the tip correction, it will resume there. Or if I was in the subroutines here, then it will resume there. Okay? So, go back to where the main loop is. And then here I change the temperature. So when I press the switch, I'm in the temperature setting mode. So I'm changing here with the pot. You can see the value is right. So I'm in this loop now, that means. And let me correct that that LED. So that's done when it says here. So we'll put the LED on, and when I press the switch again, it's still on. Okay, that's because it's flashing. So what I have to fix there, flash LED. I know this is what I've changed here. I left it that it goes to off. It goes to on the last here, on the last routine. So I swap those around. So I'll compile that. Okay. And I'll rewrite here, back to the chip. So I flash the chip again. Let's see what happens. Okay, so now when I press the switch, I'm in changing the temperature here. Go back to 250. I press the switch again, the LED's off. But there was a reason why I've changed that. I have to still work out why I did that. I was trying to work out something before. But anyway, so that was that. If I hold the switch down for 3 seconds here, hang on a minute, when it's working, hold it down for 3 seconds, it will show me what the error correction is. Here it's saying negative. It says it was 12. Okay, now the pot here, now I can change, it goes only up to 30. You can set it whatever you want, but just to show you on the here, if it's greater than 30, then the tip error is 30. In this situation, any type of similar elements to this, or let's say with the original thermocouple that I was doing with the original Weller, that one would be a bit more accurate than this, because I had the thermocouple sitting right behind, touching the tip. Okay, so that means the error correction is actually less, and the tip on the original Weller, okay, is shorter from the back too. That means I've got a shorter distance. And when I remember the first video that I did, it was very accurate, within 2 degrees, you know, the back of the tip and the front of the tip. But obviously this thermocouple is set back, and this tip has got a longer shank. Okay, so if I show you here, this tip, you see it's a longer shank. It's still a bit hot. So yeah, so back to the code here. The yeah, I made it that you can't adjust any more than 30. That means if you have a different tip or maybe a different element, the difference between where the thermocouple is, I'm allowing there only 30 degrees, and 30 degrees is a lot. So yeah, Something's happening here. Let's see what's going on. You see, I'm touching. Have I moved something here? Yeah, I've got something a bit loose here. Anyway, I'll work that out later.